Hello friends, a very good morning to all the students. Am I audible to all the students? Okay, fine. So friends, I hope you are ready to solve some more numericals of the chapter of the properties of gases. We have discussed in my yesterday's lecture some numericals of the chapter of the properties of the gases. We have discussed the processes that were the constant volume process and the constant pressure process. We have solved those numericals. In today's lecture, we are going to solve some more numericals of the different processes that will be the constant temperature process, the adiabatic process, and the polytropic process. And finally, we will be discussing one of the master numerical. There we will be discussing tremendous concepts related to the properties of the gases. And let me inform you that there is one surprise for you. So that surprise will be revealed at the end of my lecture. So let us start with the discussion related to the numericals of the properties of gases. So today the fourth numerical as per our sequence, the numerical states that the air enters a compressor at 0.2 megapascal and 30 degrees Celsius having a volume of 2 meter cube per kg is compressed to 1 megapascal isothermally. Calculate the work done, the change in internal energy as well as the heat transfer. Remember friends, this is also the numerical which was asked in the GTU examination for the 7 marks. So as per our standard practice of the presentation of the numericals, first we are mentioning the solution. Then we are mentioning step number 1, that is the given data. So first and the foremost thing which is given, that is a air is entering into a compressor. Then we are given the initial pressure of the air, that is P1 is equal to 0.2 megapascal. So converting this megapascal into pascal, so that is equal to 0.2 into 10 raised to power 6 pascal. I hope you are aware about this conversion. Next we are given the initial temperature of the air, that is T1 is equal to 30 degrees Celsius. Converting degrees Celsius into the standard SI unit, that is Kelvin. So the answer comes out, that is 303 Kelvin. Remember friends, this is the tricky point. Here we are given the volume of 2 meter cube per kg. Focus on this unit. The unit is given of the specific volume because the volume is divided by the mass. So I am writing that is the specific volume of the air, initial conditions, that is small v1. Here I have changed the notation because we have to specify it as the specific volume. So I have written small v initial state 1, that is equal to 2 meter cube per kg. Proceeding further, then we are given the air is compressed to the final pressure. And the final pressure is given, that is 1 megapascal. Again converting the megapascal into pascal. Okay, roll number 66. It is the can be considered. Okay, for density, I hope you have misunderstood the concept. So density is the mass upon volume. Roll number 66, are you getting my point? Density is mass upon volume. But in the numerical, we are given the volume. Only the change is we are given the specific volume. Fine. So let us proceed further in the given data. Then we are given the air is compressed isothermally. So on catching this term, we can understand that this is the isothermal process, and in the isothermal process, we are knowing the temperature remains constant. So I can write down the initial temperature is equal to the final temperature, that is T1 is equal to T2. So these are the given data. Proceeding further to step number 2, that is to find three parameters are required to be calculated in this numerical. First one, that is the amount of work done, W. Second is the change in internal energy, that is delta U. And third one, that is the amount of heat transfer, that is Q. I hope you are understanding all the points. Very simple. Proceeding further to our final step, that is step number 3, calculations. So since it is the isothermal process, for the isothermal process we have derived this equation for the work done, one of the important derivation. So W is equal to C ln V2 by V1, where in place of C I can write down P1 V1 because the isothermal process follows the Boyle's law. So W is equal to P1 V1 ln V2 by V1. Now in place of V2 by V1, I can write down P1 by P2. Here I have mentioned how I have got the answer of V2 by V1 is equal to P1 by P2. Remember friends, all the volumes I am considering the specific volumes. Here also specific volume at one state, and 2 also there is this specific volume. Now substituting the values of P1, V1, ln P1 by P2. Remember friends, in the calculation, in your scientific calculator, you are giving the key of log as well as the ln. Both the keys you will be seeing on your scientific calculator. So always use the key of ln. ln, that is the log to the base e. So on substituting the values of P1 V1 and ln P1 by P2, we are getting this type of the equation. And on doing the calculations, I am getting the answer, that is W is equal to minus 643.775 into 10 raised to power 3 joule per kg. Remember friends, since we are considering the volume to be specific volume per kg, the answer of work will be getting in terms of per kg. So I have written the notation unit, that is joule per kg. Converting this 10 raised to power 3 into kilojoules, so I am getting the answer minus 643.775 kilojoule per kg. Now the answer of work comes out to be negative. So again we will be writing down the comment. Negative sign shows that the work is done on the air during the process. I hope now you are perfectly understood the sign conventions of heat and work. Thus the final answer which we are getting, thus the amount of work done, that is W is equal to minus 643.775 kilojoule per kg. Remember friends, here the unit has been changed to per kg because we are given the specific volume. Moving further, now calculating the change in internal energy delta U, the standard equation delta U is equal to mCV T2 minus T1. But since the isothermal process, the temperature remains constant, so I can write down delta U is equal to 0. Very easy to calculate, just we need to understand the logic. So the final answer, thus the change in internal energy of the gas, delta U is equal to 0. Now moving further to calculate the last parameter. According to the first law of thermodynamics, I can write down Q is equal to delta U plus W. I am having the value of delta U, I am having the value of W. For isothermal process, delta U is equal to 0. We finally get Q is equal to W. We are already having the answer of W. So substituting that same value in this equation. So the amount of heat transfer Q is equal to minus 643.775 kilojoule per kg. Again, the answer of Q comes out to be negative. So we will be mentioning the comment. The negative sign shows that the heat is rejected by the air during the process. This is the final answer. That is the amount of heat transfer. Q is equal to minus 643.775 kilojoule per kg. I hope you have understood this numerical and you are getting all these answers. Dear friends, very simple numerical of the isothermal process. Just we need to understand some of the equations and the logic behind those equations. Kindly share your responses in the chat box if you have understood the numerical so that I can proceed further with the next numerical. Okay, fine. So getting the responses from the students. Thank you all. So proceeding further with the next numerical, that is numerical number 5. 1 kg of gas is compressed adiabatically by following the law PV raised to gamma, that is equal to constant, from the initial temperature of 290 Kelvin. The initial pressure of the gas is given, that is 1 bar. The initial and final volumes of the gas are given, that is 0.5 meter cube and 0.05 meter cube respectively. Find the final temperature and pressure of the gas. Assume gamma, that is equal to 1.4. So proceeding as per our standard practice solution. Step number 1, given data. Mass of the gas M, that is equal to 1 kg. See the first statement, 1 kg of gas is compressed adiabatically following the law. So in this numerical, we are given the adiabatic process and the standard equation for adiabatic process, PV raised to gamma is equal to constant. Initial temperature of the gas is given T1 290 Kelvin. Directly it is given in Kelvin, so no need to convert. Initial pressure is given 1 bar. Converting the bar into Pascal. I hope now you remember the conversion. 1 bar is equal to 10 raised to power 5 Pascal. Then you are given the initial volume of the gas, that is V1, and final volume of the gas V2. Dear friends, are you observing the notations which I am changing? In the previous example, I have written small v1 because the unit was meter cube per kg. In this numerical, it is only meter cube. So I am writing capital V1 and capital V2. I want your responses in the chat box if you are understanding how I am changing the notations of V, volume, where we need to specify the specific terms and where we need to write down the total volume. Okay, majority of the students are giving me the positive response. Thank you all. Thank you very much. So proceeding further, also we are given the value of gamma, that is equal to 1.4. Now step number 2, only 2 parameters we need to find out. First is the final temperature of the gas, that is T2, and we need to find out the final pressure of the gas, that is P2. Moving further, step number 3, that is the calculations. So for the adiabatic process, we are using the relation standard equation PV raised to gamma is equal to constant. So I can write down P1 V1 raised to gamma is equal to P2 V2 raised to gamma. From this equation, I can get the equation for P2. So that is P2 is equal to P1 into V1 by V2 raised to gamma. Dear students, in your scientific calculator, you will be seeing this type of the sign. and that is the sign which is for raise to. In the scientific calculator, you will be observing a key in which it is shown this type of the sign that represents the sign for raise to. Calculating all these values, we are getting the answer, that is P2 is equal to 2.5118 into 10 raised to power 6 Pascal. So 10 raised to 6 Pascal can be converted into megapascal. So the final answer of this numerical, that is the final pressure of the gas during the adiabatic process, that is P2 is equal to 2.5118 megapascal. Now again, for the adiabatic process also we are knowing the relationship between the temperature and the volume. So T2 by T1 is equal to V1 by V2 raised to gamma minus 1. So T2 is equal to T1 into V1 by V2 raised to gamma minus 1. We are knowing all these values. Substituting the value in the equation, we are getting the answer of T2. Thus, the final temperature of the gas during the adiabatic process, that is T2, is equal to 728.44 Kelvin. So only two parameters we need to calculate in this numerical. So we have calculated the final pressure and the final temperature. Dear students, I hope you are understanding the points and you are also calculating and you are getting the same answers as I am getting. Kindly share your responses in the chat box so that I can proceed further with the next numerical. I want the responses from majority of the students. If you are calculating and getting all the answers perfectly. Okay, some of the students are getting the similar answers as I am getting. Very good. Okay, thank you all. So in this I have got the maximum responses. Thank you all. So now friends, proceeding further to next numerical, that is numerical number 6. 1 kg of air at 9 bar pressure and 80 degrees Celsius temperature undergoes a non-flow work polytropic process. The law of expansion is given, that is PV raised to 1.1 is equal to constant. The pressure falls to 1.4 bar during the process. Calculate the final temperature, the work done, the change in internal energy, the heat exchange. Take capital R is equal to 287 joule per kg Kelvin and gamma is equal to 1.4 for air. Starting with the solution, writing down step number 1, that is given data. Firstly, we are given the mass of the air, that is m, is equal to 1 kg. Then we are given the initial pressure, that is P1 9 bar, converting the bar into Pascal. Then we are given the initial temperature of the air, that is T1 80 degrees Celsius, converting degrees Celsius into Kelvin. Then we are given the important point, that is the polytropic process. And dear friends, the equation for the polytropic process is also given, that is PV raised to 1.1 is equal to constant. So what is the value of polytropic index in this numerical? What is the value of polytropic index in this numerical? Very good students, perfect answer which I was expecting from you. Good students, thank you all. Perfect answers. Majority of the students has given me in the chat box. So I can write down the polytropic index, that is small n is equal to 1.1. Because the standard equation for polytropic process, that is PV raised to n, is equal to constant. But in this we are given PV raised to 1.1. So small n is equal to 1.1. Very easy to understand. Proceeding further, the final pressure of the air, that is P2, is equal to 1.4 bar. Converting the bar into Pascal. Capital R is given 287 joule per kg Kelvin, and gamma, that is equal to 1.4. So these are the given data. Step number 1. Proceeding further, next step number 2, that is to find. So firstly we need to calculate the final temperature of air, that is T2. Then we need to calculate the amount of work done, that is W. Third, we need to calculate the change in internal energy, that is delta U. Fourth, we need to calculate the heat transfer, that is Q. So these are the 4 parameters we need to calculate in this numerical. So starting with the calculations, for polytropic process, we are knowing the relationship between the temperature and pressure. So T2 by T1 is equal to P2 by P1 raised to n minus 1 divided by n. Remember friends, we are using the polytropic process. So we have to use the polytropic index, that is small n. Substituting the values in this equation, I'm getting the answer of T2, that is 298.069 Kelvin. Moving further, so this is the presentation of our final answer. Thus, the final temperature of the air, that is T2, is equal to 298.069 Kelvin. Now we need to calculate the amount of work done for the polytropic process. So the work done during the polytropic process, that is W is equal to mR T1 minus T2 upon n minus 1. How we have got this equation? We are knowing the equation W is equal to P1 V1 minus P2 V2 upon n minus 1. In place of P1 V1, I have substituted mR T1. In place of P2 V2, I have substituted mR T2. mR is taken common, so now the equation becomes W is equal to mR T1 minus T2 upon n minus 1. Why I am using this equation? Because already I am having the values of T1 and T2. Mass is given, capital R is given, and polytropic index is also given, so it is very easy for me to calculate W. So I am using this equation. So the answer of W I am getting, that is 157.65 kilojoule. Since I am getting the positive value of W, I will be mentioning the comment. The positive sign shows that the work is done by air during the process. Thus, noting down the final answer, thus the amount of work done, W is equal to 157.65 kilojoule. Dear students, I hope you are understanding the points and also you are calculating the answers and you are cross-checking your answers with mine answers. Kindly give me your responses in the chat box so that I can proceed further in calculating delta U and Q. Okay, fine. So majority of the students are also calculating with me. Thank you all. So moving further, calculations. Now we need to calculate delta U. So delta U standard relation, that is MCV, T2 minus T1. We are having the mass, we are having both the temperatures, but we are not having the value of CV. So first we will calculate the value of CV. So CV is equal to capital R upon gamma minus 1. Remember friends, this is the constant value and always here comes gamma. So CV is equal to R upon gamma minus 1. Substituting the values of capital R and gamma, we are getting the answer of CV, that is 717.5 joule per kg Kelvin. Remember friends, whatever answers you are writing, you must specify the units of the answer. Very important, never forget to note down the unit with the specified answer. It is very important in the numericals. So now the change in internal energy of air, delta U is equal to mc with T2 minus T1. We are having all the values, substituting the values, we are getting the answer. Delta U is equal to minus 39.413 kilojoule. So finally presenting the answer of delta U. Thus, the change in internal energy of air during the process, that is delta U is equal to minus 39.413 kilojoule. Now the fourth parameter, the amount of heat transferred during polytropic process. So we are using this equation. Q is equal to gamma minus N upon gamma minus 1 into W. Or you can use the another equation, the first law of thermodynamics, Q is equal to delta U plus W. Both these equations will be getting the same answer. So Q is equal to 118.237 kilojoule. Since we are getting the positive value of Q, we are mentioning the comment, the positive sign shows that the heat is received by the air during the process. Thus, the final answer, the amount of heat transfer Q is equal to 118.237 kilojoule. Dear students, I hope you have understood this numerical also in context of the polytropic process. Are you getting all these answers? Okay, fine. So now friends, let us proceed further to one of the typical numericals. So I have marked it as the master numerical because it is somewhat of the complicated pattern, some different approach we need to follow in order to calculate the asked parameters. So perfectly understand these numericals so that you will be getting more points out of this numerical. So this is the numerical which is asked in the GTU examination. A balloon of spherical shape 6 meter in diameter is filled with hydrogen gas at a pressure of 1 bar absolute and 20 degrees Celsius. At a later time, the pressure of the gas is 94% of its original pressure at the same temperature. Then two different cases are given which we need to calculate. In the first case, what mass of the original gas must have escaped if the dimension of the balloon is not changed. And in the second case, we need to find out the amount of heat to be removed to cause the same drop in pressure at constant volume. Take the molecular weight of hydrogen, that is capital M is equal to 2, and the specific heat at constant volume for hydrogen, that is CV, is equal to 10,400 joule per kg Kelvin. So let us understand these numericals slowly and steadily. Firstly, mentioning the solution, writing down the given data. We are given a balloon of the spherical shape. The diameter of the balloon is given, that is 6 meter. Thus, the radius is equal to half the diameter. So, I am getting the radius, that is 3 meter. The balloon is filled with the hydrogen gas. Then we are given the initial pressure, that is P1 is equal to 1 bar. So converting the bar into Pascal. Also we are given the initial temperature, that is T1 is equal to 20 degrees Celsius, converting this value into Kelvin. At the later time, the pressure of the gas is 94% of its original pressure. So I am writing the final pressure, that is equal to 94% of original pressure. So I am writing down the equation in this manner. So final pressure P2 is equal to 0.94 into P1. So that is equal to 0.94 into 1 into 10 raised to power 5 Pascal. I want your confirmations in this statement how I have calculated the value of P2. Kindly share your responses in the chat box so that I can proceed further. Have you understood how I calculated P2? Okay, fine. Many students are giving me the answer and they have understood perfectly. Thank you, students. Thank you all. So now proceeding further, writing down the given data, you are seeing that the conditions of the pressure are changed at the same temperature. So I am writing down the temperature remains constant, thus T2 is equal to T1. T1 is already given, that is 293 Kelvin. Also we are given the dimension of the balloon is not changed in case number 1. So I am taking the value, that is the volume remains constant. So thus I can write down V1 is equal to V2. Then I have given the molecular weight of hydrogen, that is capital M is equal to 2, as you are seeing in the numerical. Then we are given the specific heat of hydrogen at constant volume, that is Cv is equal to 10,400 joule per kg Kelvin. So these are the given data. I hope you have understood up till this point. Let us proceed further with step number 2, that is the mass of the original gas escape. So that is delta M. How we will be calculating delta M, that I will be discussing in third step of the calculations. And in the second case, we need to find out the amount of the heat to be removed, that is Q. So let us start with the calculations. Case number 1, volume of the spherical balloon. I hope friends you remember that the volume of the sphere, that equation is V is equal to 4 by 3 pi r cube. Volume of the sphere V is equal to 4 by 3 pi r cube. Are you remembering this equation? Okay, fine. Thank you all. Thank you very much. So V is equal to 4 by 3 pi r cube. Substituting the value of r, that is equal to 3 meter. I am getting the value or the answer for the volume. So V is equal to 4 by 3 pi into 3 raised to 3. So I am getting the answer, that is 113.097. That is meter cube. Proceeding further, since in this case the volume remains constant, because in the numerical only if we have understood, in case number 1 we have been told that the dimensions of the balloon are not changed. That means the volume remains constant. So for case number 1, I am taking the constant volume condition. So I can write down the equation, that is V1 is equal to V2, that is equal to 113.097 meter cube. Now friends, using the equation for the characteristic gas constant, that is R is equal to R0 by M. I hope you remember this equation in the derivation of the characteristic gas equation. We have substituted the value of R0, and R0, that is the universal gas constant. If you remember, And the value of universal gas constant is always constant, fixed for all the gases. So that is 8314.4 divided by the molecular weight for the hydrogen, that is 2. So I am getting the answer, that is 4157.2 joule per kg Kelvin. Have you understood up till here? Have you understood up till here? Okay, fine. So let us proceed further in the derivation. Now applying the perfect gas equation at the initial state, that is P1V1 is equal to mRT1. We are having all the values, so we will be finding out the value of the initial mass which is stored in the spherical balloon, or the initial mass of the hydrogen in the spherical balloon, that is M1, and we are getting the answer, that is 9.285 kg. So this is the answer for the M1 initial conditions. Moving further in the calculations, applying the perfect gas equation at the final state. So I can write down the equation P2V2 is equal to mRT2 M2 R into T2. We are having the value of P2, V2 capital R is constant, and T2 also we are having. So now we will be calculating the value of M2. So I am getting the answer of M2, that is 8.728 kg. Thus, the first parameter which needs to be calculated now, the mass of the hydrogen gas which is escaped from the balloon, that is delta M, is equal to the initial mass minus the final mass. So I can get the answer how much mass has been escaped from the balloon. So I am having the values of M1 and M2, substituting both the values, I am getting the answer. Thus, the mass of the original gas which must have escaped from the balloon, if the dimension is not changed, that is delta M is equal to 0.557 kg. I want your confirmations in the chat box if you have understood the steps, how we have calculated delta M and the first parameter. I want the responses from the majority of the students in the chat box. Okay, fine. Thank you all. So proceeding further in calculating the second parameter, case number 2. In the case number 2, it is directly given that the volume of the spherical balloon remains constant. So we are already given that it is the constant volume process, and we need to find out the amount of heat transfer in constant volume process. So firstly, we are using the combined gas law at the initial stage and the final stage. So that is P1V1 by T1 is equal to P2V2 by T2. Thus P1 by T1 is equal to P2 by T2 since the volume remains constant. So calculating the value of T2. Now the amount of heat transfer, that is Q is equal to mCV T2 minus T1. Considering the original mass, because we need to consider the original conditions of the hydrogen gas which is filled in the balloon. So we will be considering the mass, that is M1. So Q is equal to M1 into CVT2 minus T1. Substituting all these values, we are getting the answer Q is equal to minus 1.69 megajoule, negative sign, the same comment. Thus the final answer Q is equal to minus 1.69 megajoule. Okay, so this is the answer, and the last surprise for you. These are the numericals for your practice. So kindly take the screenshot of these numericals. In the next lecture, all the students must calculate these numericals. I will be asking the answers of these numericals. While calculating, if you are facing any problem, you can ask me by WhatsApp